All right, ladies and gentlemen, class recording has started. So, back on Thursday, we introduced Chapter 5 in Section 5.1, getting into Newton's laws. We talked about Newton's first law and Newton's second law. So, Newton's first law can be summarized in one word, and that one word that summarizes Newton's first law is inertia, right? The tendency of an object to maintain what it is currently doing, whether that is at rest or whether that is moving with constant velocity. And the two key points of Newton's first law are summarized by these two key points here, right? It says an object at rest remains at rest as long as no net force acts on it. An object moving with constant velocity continues to move with the same speed in the same direction as long as no net force acts on it. The two key points being there, and we'll get into this a little bit more today, no net force. So we had to define net force. What was our definition of net force? How did we define net force? Right, good. The sum of all forces. And because forces are vector quantities, another way we can think about it is as the what? The resultant force. That could mean that it's the hypotenuse of a right triangle, or it could just mean it's two forces added together, right? That depends on how the forces are oriented to one another and stuff like that, okay? All right, that being the case, at the top of page 4 of your packets, it says, practice problem number 1, concept check. It said, is it possible for an object at rest to have one force acting on it? If your answer is yes, provide an example. If your answer is no, explain why not. So, is it possible for an object at rest to have one force acting on it? This is the top of page 4 of your packet. Any thoughts? Is it possible for an object at rest to have one force acting on it? Okay, so if it's good. Okay, so the correct answer is no. All right, it cannot have only one force acting on it because Newton's first law says that an object at rest remains at rest as long as there is no net force. Net force is a vector sum, meaning that in order for us to have no net force, the vector sum has to be what? 0. In order for us to have a sum equal to 0, we have to have at least how many forces? 2. One positive, one negative. That would be the easiest way to do it. Okay? But if an object only has one force acting on it, right, could its vector sum be 0? Can't be. So there would be some net force on it, and therefore it wouldn't remain at rest. Okay? Good there? That then brings us to the second idea that we talked about on Friday that we introduced. We introduced Newton's second law. If Newton's first law can be summarized in one word, that word being inertia, Newton's second law can also be summarized in one word, maybe not as neatly as inertia, but there's one. What does Newton's second law tell us about? If inertia is something not changing, then Newton's second law tells us about, not exactly, although force plays a role. If Newton's first law is things not changing, things staying the same, inertia, Newton's second law would be things changing. And what word do we use to describe things changing? Acceleration. So Newton's second law tells us about acceleration. But we saw on Friday that when we're talking about acceleration, we also have to discuss two other factors. What are the two factors that affect acceleration? Force and mass, right? What kind of relationship do force and acceleration have? Force and acceleration have a direct relationship. If we look at the top of page 3, right, Figure 5.3, acceleration is proportional to force. If we push harder, there will be more acceleration, so direct relationship. On the other hand, what kind of relationship do mass and acceleration have? Inverse. The more mass there is, the less acceleration there will be. That's summarized in figure 5.4. Those two relationships come together in this fraction. A is equal to F divided by M, right? Where acceleration is equal to force over mass, where that summarizes those two relationships. The direct relationship between force and acceleration, and the inverse relationship between mass and acceleration. Usually, we will see it in this form, F equals ma. Same things hold true there. Okay? We also talked about on Friday that very rarely will we have just one force that we have to consider. So when that's the case, when we have to consider multiple forces, we don't just look at the force, we have to look at what? The net force. And on page 5 of your packet, right, second law also applies to net force, right? We use the notation, the Greek letter sigma, sigma F, to represent the sum of the forces, or the net force. So Newton's second law, more generally, is stated as sigma F is equal to m times a, where the sum of the forces, the vector sum of the forces, is equal to m times the mass times acceleration. Okay? Good there. We will talk a lot more about that over the next, starting next week when we get into applications of Newton's second law. But today, I wanted to make sure that we had some concepts down, make sure that we understand these things in the application of just the laws themselves, not numerically necessarily, but just from a conceptual standpoint. So, that being the case, I'm going to show you this website here, which is called polleverywhere.com. So Poll Everywhere is a data gathering website. It basically does polls, but it gathers information from cell phones. You are going to send text messages to this website, and that website will then tally up all the information that you send it, and it will provide us with a bar graph that represents your responses to those questions. Okay? For example, this isn't related to Newton's first law or Newton's second law in any way, shape, or form, but just as a practice, let's go here. So, I did. I mean, it's pretty fast. So, well, that's not the food, that's the line. I mean, so. All right. So up on the board, it gives you a question. It says, what's your favorite fast food restaurant out of the following? And it gives you 4 choices. So here's what you're going to do. You're going to send a text message. So open up a blank text message. And you are going to send the text message to 37607. So that will be in the to line of your text message. Okay? Then in the body of your text message, you're going to include one of these 6-digit codes. So send this text message to 37607, and then in the body of the text message, you're going to include one of these 6-digit codes to represent your choice. And when it receives text messages, it automatically starts tallying the results so we can see how you guys voted. All right? I believe that's the first vote that McDonald's has gotten all day long. So. See, Chick-fil-A, I mean, I really like some Chick-fil-A, but I have, some moral opposition to their, stance on things, so.
I don't think that really has to do with their food.
Well, I don't want to give people money that, have views that are, in opposition to mine, so.
I feel bad, so their food is very good.
Okay, so out of the 5. I like Chick-fil-A. I'm not saying I don't like Chick-fil-A. I really do like Chick-fil-A, but, so.
Those are definitely the top 4, except for McDonald's.
See, Taco Bell is just, whew.
Taco Bell is so good.
I can't even remember the last time I actually had Taco Bell. So what? Qdoba? Is there any? Is there? Okay. So Qdoba. So yeah. I'm actually a little disappointed Jimmy John's didn't get any votes, but yeah. Jimmy John's is really good. So and it's freaky fast. I mean, it is. I mean, like seriously, sometimes you go in there when nobody's in there. By the time you finish paying and walk down to it's already done. I don't have sliced turkey and sprouts and guacamole at home. So what? Oh, Chipotle. I always get the same thing when I go to Jimmy John's too. So the Beach Club, number 12. It's so good. So good. Penn Station. See, that's kind of far away. But I mean, anyway, so that's how it works. Okay. So you're going to continue sending messages to 37607. So if you have that, cause it's actually, I believe it should have started a conversation with you and says, hey, you voted in a poll, right? No, it didn't send you. Oh, no. Okay, so yeah, I mean that might be that too. So yeah. All right. So your first question that you're going to answer for me is actually question number 1 from the sheet that I just gave you. Okay? So what I'm going to do here first is I'm actually going to hide the bar graph. So you will not see people's responses as they come in. So you can't be like, oh, well, everybody else chose that one, I'll choose that one too. Okay? So here's your first question. Like I said, it's the first question off of the sheet that I just gave you today. All right? Do we need to see that, or does everybody see what they're looking at? You want me to show it to you up here? Or? Good. So. Okay. All right, so it says, which of the following situations does not require net force? So again, you're going to send a text message to 37607, and in the body of the text message, you're going to put one of these 6-digit codes. So which of the following situations does not require net force? I've received one result so far. So. I don't have an actual product right here. So. 4.
I'm just gonna like pile it up there.
So that's the point, is that we don't need you to tally.
No, but like I'll just write my tally.
Oh, okay. So, you can just tell us. How about this? How about I'll ask you for your answer to the question, and we'll see how it compares to everybody else's responses.
I like that. By myself.
All right, are we ready for the reveal of the results of this poll? No, sorry, it's completely anonymous. I can't tell. There is a pay service that you can provide, or you can buy a subscription, and that will let people like sign in basically. So in a way, I could really do tests this way if I really wanted to, where you guys like, I could just do it, and it'll tell me who gave which response and stuff like that. So, but I don't want to pay for that. So, all right. Yeah, just text me. Well, that's true. So, yeah. But you don't know if it doesn't tell you whether you're right or not. So. All right. So we said that Newton's first law states that an object will remain at rest or moving with a constant velocity in the same speed, same direction, as long as there is no net force. Basically, net force causes something to accelerate. If there is no net force, there will be no acceleration. We talked about back in chapter 3 that there are 3 things that could be acceleration, right? What are the 3 things that could be acceleration? Speeding up, slowing down, changing directions. All 3 of those are acceleration. Therefore, an object starting to move, an object stopping moving, and an object going around a corner at a constant speed. Even though it says constant speed, that last one is still acceleration. So the only one of these 4 that does not require a net force is an object at rest. That's you. This is your. This is what, like, for your reference. Yeah. Your open note quiz that you have this would fall into that category of things you can use for the open note portion of the open note. All right, good there. Questions on that one? All right, we are going to skip then to question number 3 on your sheet. Okay. And it says, if a hockey puck is moving on a completely frictionless patch of ice, it will eventually slow down because of its inertia, the tendency for an object to remain at rest. So, is that statement true or false? If a hockey puck is moving on a completely frictionless patch of ice, it will eventually slow down because of its inertia, the tendency of an object to remain at rest. Is that statement true or false? Give it another second here. All right. All right. Results reveal. Okay. So, good. All right. We talked about that inertia actually encompasses 2 things, right? Sorry. Correct answer to this is false. That is a false statement, right? Inertia actually encompasses 2 situations, right? It's an object at rest, but it's also an object in motion, right? Inertia doesn't say that objects will come to rest. Inertia says that objects will continue doing whatever they are currently doing, right? So if there's completely frictionless and the hockey puck is already moving, it will continue to move. Good there. Okay. Yes, sir. Go ahead. Yep. Actually, I had to, but I decided not to do it because I wanted to change something about it. Okay? So, this is number 2, seeing as how Simran asked. Okay. So it says, what causes a moving object to go around a curve? What causes a moving object to go around a curve? Well, you could, I mean, if you want to, because it's pulled up and ready to go. So, but I'll let you guys answer it, and then I'll tell you why I skipped it originally. Oh, sorry. Yeah, this has been doing this. I don't know why. Oh, I know why. All right. So, what causes a moving object to go around a curve? You guys are slow. Yeah. I mean, well, I think this question actually would be a good example of why I'm doing this. So, I'll give it another second here and see if we can get these last couple of results in. Okay. So here is your answers. Okay. Here's why I do this. Here's why I like this activity. Because if we just did this sort of normal, I would, take the question and give you guys a chance to kind of answer it. And then somebody would give me the answer, and I would say, is that good? And everyone would be like, yeah. However, now with this, I know that half of the people in this room don't know the right answer to this question. All right, so let's discuss. Technically, none of these answers are the correct answer. Let's say. That's accurate. However, the best answer out of the choices given would be force. Force causes things to accelerate. When an object goes around a curve, that is acceleration. But acceleration is a measure of how much it's changing, not what So the best answer of the four given would be force. However, you technically should change that choice to say what? Net force, right? We may have multiple forces acting on an object, and it may do nothing. It may not change at all, because they may cancel each other out. So technically, the best answer for this question would be net force. Okay? How's that? Does that make sense? All right. You think? No, I don't actually. So I'll show you that in a little. I'll show you that in a little while. So. All right. On your sheet, number 4, there is a picture that has an object that shows multiple forces acting on it. Which best describes the acceleration of the object experiencing those multiple forces?
Why is that not the sheet?
Yeah, I don't know. It's kind of weird. Sometimes that thing. Question number 4, there's a picture next to question number 4 on your sheet that shows an object with multiple forces acting on it. And so based on that picture, what would you say about the acceleration of the object? There's only one answer. I'll tell you how you affect the situation. I'm pretty sure every question I've given you from this point forward has been corrected. All right. So the acceleration of that object in question number 4. All right. Correct answer in that question is 0. Right? Now, you have to make an assumption there, right? Those two forces that are labeled in question number 4 are both labeled as what? F. And even though it doesn't give you a value, if we have F that shows up twice on the same drawing, we can assume that they're the same thing, except one is labeled as F and one is labeled as negative F, right? So the net force acting on that object is going to end up being what? 0. The vector sum is 0, and therefore the acceleration is 0. Okay? Question number 5 builds off of that question. Which of the following best describes the motion of the object in question number 4? So same picture, same object, same forces, but now it's asking you about that object's motion. I would say that this question is probably the hardest question on the sheet. Okay? And here's why. Okay? Correct answer to this question is D. Can't be determined. We said that net force means that the acceleration is 0. But acceleration measures change, right? There are 2 choices up there that represent no, or that describe no change. At rest is something not changing, but also constant velocity in the positive direction is also no change or no acceleration. From a force standpoint, we can't really tell the difference between an object at rest or an object moving with a constant velocity, because Newton's first law says those are exactly the same. They're both an object not changing or not accelerating. So, if you see an object that has a 0 net force, you cannot automatically assume that it is at rest. You can assume that it is not accelerating, but that could mean at rest, or it could mean moving with a constant velocity. It's not accelerating, but that doesn't mean it's not moving. For example, right? Okay, here's this cart, right? Okay. As it's sitting here, just on the track, no acceleration, it's at rest, right? So to get it to start moving, I have to push it, right? That's acceleration. But as soon, so there are two forces acting on this cart. Gravity's pulling down, and then the track itself is actually pushing up on it. Because if gravity was the only thing acting on it, what would it do? If gravity's the only thing acting on something, what does it do? Right? And as it falls, it accelerates. How fast? 9.81. That's not happening to this, right? So there is no net force acting on it. Gravity pulls down, the track itself pushes up, they cancel each other out. No net force. If I give it a push to the right, my right, your left, it will start accelerating, but only as long as I'm pushing it. Okay? After I let it go, what does it do? It remains at a constant velocity as long as there's no other forces acting on it, right? There's a little bit of friction here, right? Although in this one, even if we took a motion detector and measured it, right, we would see that this stays pretty constant as it goes along. Eventually it would stop because there is some friction, but it's pretty small. Okay? But if we looked at the forces on it while it was moving along the track, yep, gravity and the track are still acting on it. They're canceling each other out, but that's not causing the object to change when it's moving. Does that make sense? Simmer, go ahead. Yep. 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 So the force is causing what kind of acceleration then? Negative acceleration. And to do that, it has to act in which direction? The negative direction. So if we call the direction that this cart is moving the positive direction, something opposing it would have to act, or something in the opposite direction would have to cause it to stop, right? So, right, to get it to stop, I have to push it this way. Right, because even friction is a force, and we'll talk about that more in 5.3, but the friction is generally a negative force, so it causes negative acceleration and generally causes stuff to slow down. Eventually it would, yes. Okay, and then we'll get into talk a little, that gets a little tricky, especially at the end, and we'll save that for section 5.3. Not in that picture, right? In that picture in question number 4, the only two forces that you know about are those two forces, and they're exactly the same in opposite direction. So you can't assume that it would slow down in that picture. Okay? You can't say, oh, well, there must be friction there. Well, it's not on the picture, so you can't really assume that. Or it might be a situation like this. Okay? There's friction acting on this in the opposite direction, but I'm pushing it in the direction that it's going, right? So the friction is acting on that, but if I push just as hard as friction is pushing in the opposite direction, this object will not speed up or slow down. So it just continues to move at a constant velocity right across the table, just like that. Does that make sense? Okay. So yeah, friction generally causes them to slow down if friction is the only thing acting on them. If you have something to counteract friction, it won't slow down. All right, good there? All right, I'm going to skip. Which one am I going to skip? I'm going to skip 7 and go straight to 10. That's the next one I want to show for you. Okay. All right. So it says, number 10 gives you 4 velocity graphs. And it says, which of the velocity graphs in number 10 best describes the motion of an object pulled from rest with a constant force? I will tell you that that constant force at the end, it should say pulled from rest with a constant net force. You can add that in. So which of the velocity graphs in number 10 best describes the motion of an object pulled from rest with a constant net force? Yes, I think, yeah. So, it's a little better than what we did. Yeah, but, all right, so the key to this question is, right, constant net force, Luke, means what? Constant acceleration, right? First, let me go here. First, I'll show you the results. Okay, correct answer to this question is graph A. Graph A is the correct answer to represent motion of an object pulled from rest with a constant acceleration. If we go, oh, I don't even have it up. Okay. First, if it tells you that it was pulled from rest, that eliminates one of the choices right away. Which choice does it eliminate right away? C. C doesn't start from rest, right? It doesn't start at 0. Okay? But constant net force means constant acceleration. Going back to chapter 3, what does constant acceleration look like on a velocity graph? It's linear. That's A. Okay? Just so the last one we were going to do was 11. Correct answer to 11 is B. So take a look at that. All right. Enjoy your day off tomorrow. It is wording-wise, but these are position graphs and those are velocity graphs. Okay. 10 is A and 11 is B, because B has that parabolic shape, right?
Yeah, I just wasn't sure.
Yep. That's the one. So, all right. Hey, enjoy your day off tomorrow, everybody. I'll see you guys on Wednesday. We'll lab it up on Wednesday. So.